But you'll be super duper happy to know there's very little, like, actual trig in this chapter. Sine and cosine, we're going to take a little bit of a break from sine and cosine for a while. Yes, dear. Not super much. It's like a totally kind of different way of looking at stuff. So, like, it's going to feel like kind of a mental break for us. It's a little meant to be. All right. So what we're going to be talking about, this is actually chapter 10 in the book. This is going to be sequences and series. There we go. All right. My turn now. So we're going to talk about sequences to start. And what a sequence is a list of things, usually numbers, especially, since it's math class, in order. So it's that is too skinny of a pen. Hang on a second. Boop. A sequence is a list of terms that are in order. So, for example, we could have a sequence that looks like 3 and then 5 and then 7 and then 9, and I could continue. When we are writing it as a sequence, we're going to put it in our curly brackets, and that makes it a sequence. So we're going to have a couple of different kinds of sequences. We're going to have an infinite sequence, which will go on forever. I mean, your notes. Can I physically write something that's infinite? No. So what we do when something's infinite, we have the ... The ellipses will mean it's infinite. It's continuing on in this pattern. Versus something that's finite. It is the opposite of infinite. It ends. So it ends somewhere. That is a terrible... There we go. Ends somewhere. So a lot of times we're going to talk about these things and talk about like which number term we have. So this one right here, our very first piece we have in our bracket, this would be our first term. I know sometimes I feel like I'm giving you super tricky information here. So the 5 in this sequence would be the second term. I know, I'm giving you such complicated things. Oh my gosh, I am the worst ever. So the 7th would be our third term. Oh my gosh, what? And it will continue on. So a lot of times we're going to talk about the nth term. This thing, nth term. And that would be any term in the sequence. And a lot of times we're going to write it. I'm going to write this down. Any term in the sequence. It's part of the reason I write with you guys, is it stops me from talking too darn fast and getting too far ahead of you. That's part of the reason I write with you. So a lot of times we're going to write our sequences as a sub n. A sub 1. So that would be our first term. A sub 2, that would be our second term. A sub 3, that would be our third term. And if we have a finite sequence, even if it's really long, we might still use our ... but it's going to end at a sub n. So we'll usually put the first 2 or 3, and then we'll put the last one if we have a finite sequence. If it is infinite, we might put our a sub n and then do another dot, dot, dot. So that would be for infinite. Finite is ending there. And a sequence has a rule used to find the value of each term. Usually it's a function rule, like this would be plus 2, plus 2, plus 2. So it would be 2n with our starting amount plus 1. So we could find the linear equation for this pattern because 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 2 is 9. So a sequence has a rule, usually a function, not making a guarantee. Used to find the value that looks like valve. Used to find the value of each term. So a lot of times we're going to be given information, we're going to be given equations, we're going to be given pieces that we need to have. So I'm going to start by showing us a couple of function rules. We're going to use it to find the first few values. So I'm going to give you guys a little bit of time to write this down because I also forgot to bring my water. So. So what we're going to do next is I'm going to give us a function rule. So we're going to get a rule for our sequence, and we're going to find the first 4. We're going to find a sub 1, a sub 2, a sub 3, and a sub 4. So the first 4 values. So this would be an example of a function, or of a sequence. So we're going to find the first 4 terms of the sequence, n equals 1 through n equals 4, of n over n plus 1. So the first thing we're going to find is if n equals 1. That's going to give us a sub 1 because n is 1. So if we substitute that pieces in, n, 1. n plus 1, 1 plus 1. What is 1 over 1 plus 1?
1 over 2.
1 over 2, 1/2. So our first term, a sub 1, is 1/2. If n equals 2, that's going to give us a sub 2. Our numerator, whoop, that's not the laser pointer. Our numerator, that's our n, so our n was 2. Our denominator is 2 plus 1. 2 plus 1, bless you. So that's going to be 2/3. So if n equals 3, to get a sub 3, what are we going to have? 3/4. What about n of 4? What's a sub 4? 4 over 5. So we're going to write it as a sequence, meaning we're going to put it in our curly brackets. We're just going to set them up. 1, 2, 3, 4. So we're going to put our 1/2, then 2/3, then 3/4, there's a 4, then our 4/5, and this doesn't really stop, so it just kind of keeps going, dot, dot, dot. That's our sequence. Yes, dear. we will tell you if it's infinite or finite, or we'll kind of look at it. If it ends and it gets to a point where we can't keep going, that would be finite.
Wait, so like if you got like something that did not exist,
Like if we wound up, if it was like n over n minus 1, we would not be able to do a sub 1 because we'd have a denominator of 0, it wouldn't work. So that, now you're approaching significantly higher levels of math. So we're not going to give you that. Everything we do should work. And as for right now, I believe everything we're going to do is going to be infinite for a while. Been a minute, I haven't looked that far ahead. Good job.
So like, undefined, then how would it like still be going in order?
It should not happen in the middle where it would be undefined.
What do you mean?
You should never wind up with something especially undefined over here. If we had something that got undefined, it would either be the very, very first or the very, very last. And in which case, we won't assign you that, like, because that's significantly higher. Like you're talking Calc 3 stuff. So I'm not going to have you figure something out where it's undefined and we have to do anything with it, unless it's just say it's undefined and this won't work. That would be it, but it shouldn't happen. So let's look at another one, another way that we might see a function rule. That's what we did. We found our first 4 terms in the sequence. I'm going to give us a different rule, but the same instructions, the first 4 terms. So they're not always going to be pretty. So we're finding our first 4 terms in the sequence for 2 plus 0.1 to the power of n. So for a sub 1, for our very first term, that's when we have our n being 1. So we're going to have our 2 plus 0.1 to the power of 1. So 2.1. For a sub 2, we're going to have our 2 plus our 0.1 squared. If it helps, you could also think of this as 1/10 squared. 0.01. So this is going to be 2.01. So a sub 3, 2.001. So then our a sub 4, 0.001. What do you mean? What do you mean get a 4? Oh, this is saying, so n equals 4 is this n right here, a sub n. So think about these as a sub n. Okay, so that's where we're putting that n equals 1. That's our first piece here versus our fourth piece here. So first piece through fourth piece. So writing this as a sequence, we would have, just putting them in order, just pull it out of the package, dude. That is the noisiest crinkle of all the possible crinkles. Yep. Just writing them in order. 0, 0, 1. And then, oh, I am running out of space. 2.0001. Dot, dot, dot. Squiggle. Squish. That is a terrible squiggle, but it gives the vibe. I do not care how pretty your squiggle brackets are. I don't care if they look like that.
I think it gets to a point.
Oh, I guarantee you I will have seen worse. Think of it like writing a quarter rest in music. It's very similar vibes of, hey, we get the vibe. Okay, so sometimes we can do these mentally. All right, we're gonna do another one. Sometimes they're gross looking. So sometimes they get a little complicated, but we can still do this. It's still doing the same thing. We're still going to find our a sub n. So we're going to start by finding a sub 1. We've got our set here. This is our new sequence. We've got -1 to the n plus 1 times n squared over 3n minus 1. What's that? I changed it. I told you we're going to do another one. Here's another one. Oh, man. I know. We went from adding to squaring and multiplying and all kinds of things. It's almost like you guys are doing some hard math stuff. What? Shock. Oh, my gosh. Say it again. It should not be 0. So we've got our n of 1. We're substituting 1 in every place we have an n. So we're going to have our -1 to the power of 1 plus 1. I'm going to switch my, so this is my n of 1. And then we've got our times the fraction, where we've got our 1 squared over 3 times 1 minus 1.
1 squared is 1, that's 1/2.
I know, I was just filling it in. You're just jumping ahead of me.
It's 1/2.
It is. Because our -1 to the power of 1 plus 1, so -1 squared gives us 1. 1 squared over 3 minus 1 is 1/2. So we have 1 times 1/2. So this one simplifies down to be 1/2. So very similar vibe. We're going to take our a sub 2 because we're finding our first 4 terms. So we're going to have our -1 to the power of 2 plus 1 times our 2 squared because our -1 to the third gives us -1. And our 2 squared over 6 minus 1 gives us 4/5. So it equals -4/5. So looks gross, definitely doable. Same thing for a sub 3 for our third term. A sub 3. So substitute all your pieces in. What do we get for a sub 3? 9/8. Okay, and then do a sub 4. This formula? No. This is a pattern, just like I gave us on the last one that was our 2 plus 0.1 to the n, n over n plus 1. This is not a memorized thing. This is a equation we give you. It's just like me saying, find our slope and intercept of 2x plus 7. This is a problem, not a memorization thing. But our, you okay? Our a sub 4 was our -16 over 11. So our last bit, I'm going to write this as a sequence. We're just taking our answers, our simplified answers. So we'll have our 1/2, then our -4/5, then our 9/8, then our -16 over 11. And this pattern will continue. So dot, 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 squiggle.
Yeah, I agree.
Okay, questions on this one? Because this one is the grossest one of the day.
Really?
It is.
What?
The next one's gonna feel like I'm tricking you.
I'm scared. Why is it that easy?
Oh,
4? 4?
4.
4.
This is 4 all the way.
I was gonna say, so what is a sub 1?
4.
4.
So it's a lie?
What is a sub 2?
4.
4. Y'all caught on that way faster than my last couple of years have caught on to that one. Equals 4. There's no n to substitute in. It just is 4. So it would, if we were trying to graph this, it would be a line. But it's a sequence because we're going to do things with them eventually. Because eventually we're going to do like sums of them. These,
Because you just read that 4.
it would just be 4. So our sequence, if I was to write this out, all first 4 terms, we'd have our 4, comma, 4, comma, 4, comma, 4. And it continues. It's just stuck. It's just like it's stuck at 4. So you had a robot that was stuck there going beep. 4, 4, 4.
You can be a good robot.
I know. I miss my calling sometimes. Okay, so when we're given kind of a function rule, we can do that.
Yeah.
See how it's worded on the next page before I start talking. Okay. So we're not always just going to straight up hand you a formula and say, just plug in these numbers and go.
Are we done?
No.
Oh.
You wish.
We still got more than 15 minutes. Sometimes we're going to give you something called a recursively defined sequence.
4.
4. And what a recursively defined sequence does is it bases our answer off of the previous number. So if I like doubled every time, I mean, I know that we know how to do that as an exponential, but if I said I have $2 and tomorrow it doubles, I have $4, and the next day it doubles, I'm taking my 4 times the 2. The next day it doubles, I'm taking my 8 times the 2. So it's based off of the previous day's stuff, based off the previous answers things. So it's tying our pieces together as a recursively defined function is the way it's called. So I'm going to give us an example of one. And when we have a recursively defined function, we're going to be given a term and an equation. So, because I sometimes wind up going too fast on these because I use these in like my homework and stuff. And so I sometimes just like hit the gas, get through it. I'm trying to slow myself down on it. So a lot of times we're going to be given a formula that talks about a to the k plus 1. And what it is it's taking a term and we're getting the next term based off of if I have a sub 1, I can find 2 based off of that. So we're letting k equal 1. Here. So we'll give you pieces like this. We've got a sub 1 equals 3. So the first term exists. It's a thing, it's there. So I can find any term I want using this equation here. A sub k plus 1 is 2 times whatever the previous term was. So we're going to write out the first 4 terms here. We have a sub 1. We want to get all the way up to a sub 4. And then we're going to see if we can write kind of a generic equation. We're going to see if we can find the pattern. So if we want to get a sub 2, right? That's the next thing because we already have a sub 1. I can rewrite a sub 2 as a sub 1 plus 1. That's the same thing. 1 plus 1 equals 2, right? Well, now what we have is I have k being 1. So if I follow that equation, this is going to be the same thing as 2 times a sub 1. But we know a sub 1. A sub 1 is 3. That's this guy here. So this whole thing's going to equal 6. So a sub 2 equals 6. Nope, I'm going to do that with a different color. Blue. So a sub 2 equals 6. I already used blue too. Goodness, I need a different color. There we go, green. I used blue, I used purple. So then we can do the same thing for a sub 3. I can write a sub 3 as 2 plus 1. That'll let me use the previous value as my a sub k, because we can use this equation 2 times a sub 2. But now we know a sub 2 because we already figured it out. 2 times that 6 that we found. So what does this one equal? 12. So it's basing them off of the previous answer. Most of the time. Sometimes it will vary. I'm trying to think of when we do that. We'll see a touch of them tomorrow, but not tons. Okay, most of the time it is going to be a plus 1, because that is what this is doing is this is setting you up for a kind of proof that happens later on. It's called a proof by induction, where we base it off of the previous terms. So this is kind of setting us up towards a calculus style proof. So it's building up towards that. So let's do one more term on here, and then we'll see if we can figure out what our pattern is and why the heck we have this. So let's do a sub 4. Yep, 2 times our a sub 3, which is the same thing as 2 times that 12, which is 24. So we have our a sub 4 is 24. So if we wrote this as a sequence, we would have our 3 and then our 6, comma 6, comma 12, and then 24, and it would, continue. So what's happening between them? It's doubling. It's multiplying by 2. So could we write a kind of generic equation for like an a sub n? Yeah, we can. Because we know it's doubling. So how would I write an equation and say that it's going to double? I was going to say, we want to be able to just plug in n. I want to be able to go and say, I don't want to have to find everything between here and, let's say I want a sub 30. I do not want to have to figure out all the pieces in between. I would love to be able to just substitute in 30 and get my answer. So could we write a function rule that will just use n? So not using a sub n, just n. So I want to be able to substitute in 2 directly and get 6, or substitute in 4 directly and get 24. So we know it's multiplying by 2 each time, right? Times 2, times 2, times 2. What kind of function multiplies by 2 every time? Linear, quadratic, exponential. What do we got? What's up?
Why do we assume that AK is 1?
We are given this first piece here, so that's where we start. Because I want to find 2. So I know 2 is the same thing as here. K is an anything. It's just a variable. So we're basing it off of the piece we have here. It's not that K is 1, it's that I'm going to substitute in 1 for K, and that'll give me 2. If I substitute in 2 for K, it gives me 3.
Oh, so we have to make sure that
It's lining up, yes. Cool, cool. So if we multiply by 2 every time, that's going to be an exponential function. 2 to the n, right? How much do we start with? What's our starting amount of an exponential? The first piece we have is 3. But if I take 2 or 3 times 2 to the n, do I get 3? For like 1, if I do 3 times 2 to the first? No. What do I get? We get 6. If I put in 2 here, trying to get a sub 2, 3 times 2 squared gives us the next one down. So we're off a number. So I'm not actually going to put n as my power. I need one less. N minus 1. So if I calculate using our n's here, so n1, 2 to the 0 gives us our 1. 2 to the power of 1 gives us a sub 2. So trying to find these patterns is a little tricksy.
How did you know it was the x to b?
Since we looked at our list down here, or we look at our list of numbers, and I say 3 to 6 to 12 to 24, how is it changing? Well, 3 times 2 gives me 6, times 2 gives me 12, times 2 gives me 24. So that tells me that this is going to be an exponential with a base of 2. Our starting amount, the first piece we have is right there. Whenever we have an exponential, we're probably gonna base our a sub 1 in it. And just seeing if we can figure out our pieces. I was looking at the next ones. Okay. We're gonna just do the finding the next 4 terms in this next one, and that'll be where we stop. Okay, we're not gonna get to the equation on it because it's gross. So we're gonna find our first 4 terms, and then we'll call it good. I can show you the equation if you want, but finding it's a pain. So if we now tell you that we have a sub 1 is 5, and I can find a sub k plus 1 as k times a sub k. So our very first piece, we're going to use the one we have. So we're going to let k equal 1. So, and that's another one. So if k equals 1, because that's what we have here. And this is just another way to kind of think about it and write it, just because I know we got all this stuff. So if we have 1 plus 1, our k is 1, and we have times a sub 1. So if we let k equals 1, that tells us a sub 2, because 1 plus 1 is 2, equals 1 times our a sub 1. A sub 1 is 5. So we get that a sub 2 is 5. Right? So it's just kind of another way of writing it. Whatever works for your brain works for me. Because then we're going to keep going. We've got a sub 1. We've got a sub 2. Let's get a sub 3. So if we have a sub 1, sorry, 2 plus 1. We've already done 1. Yeah, we're going to have 2 times a sub 2. So a sub 2 is 5, so this becomes that a sub 3 equals 2 times 5, which is 10. So a sub 3 equals 10. So then we'll have our A sub 3 plus 1. Because that's going to give us A sub 4. That's what we want. That's going to be our so the A, this one here, we picked it. It's the only one we have information for. What K is always going to start with whatever we're given. I'm never going to give you this and have you just have to make it up. We're going to be given information to fill it in the first time.
But like, I don't get why K equals 1.
It's not that K equals 1. We're just going to start with K equals 1 because on this one, K equals 2. On this one, K equals 3. We're doing different substitutions. So this one is that, whoop, that's not a pen. This one has K equals 2. This one has K equals 3. Because then when I simplify this, let me finish writing here, 3. This gives us A sub 4, because 3 plus 1 is 4. But we get that from our 3 times our A sub 3, which was 10. So our sequence here is A sub 1 was 5, A sub 2 was 5, A sub 3 is 10, A sub 4 is 30. And it would continue on, squiggly bracket. The equation for this one is kind of gross. It involves a factorial. Because it's giving us kind of a Fibonacci sequence-esque vibe. Okay, so we're going to keep working with our recursive functions tomorrow. There's our homework. Does it have a K up there? Hey, it does. Oh, it's an entirely different font. That's always so weird to me. It is an entirely different font between my screen and the iPad. Mine also is missing the K on homework, but yours is not, even though this is in charge of that. I love it so much.